Hello, everybody. Welcome back to another discussion dynamics. Today we will continue kinetics of rigid bodies, as you can see. Plan for today is very brief lecture review and then two examples. Without further ado, let's dive straight into our discussion. Let's start with brief lecture review, which is here. So, what do we have in here? I would like to start with reminding you what we were talking about last time. So last time we had a rigid body, and we just had some force acting on our body. It's a net force, yes. So it can be external force, it can be force coming from gravity, it can be force coming from constraints, right? And then we also had some. So these forces can cause net force and net moment acting on our body, yes? And this is always true to express the motion on our body in this way. So net force will result in m times AC, where C is center of mass, and you can always sum moments about point C, and you can equal them to IC times alpha body. This is what was happening last time, yes? However, today we will be talking about a very specific variation of this equation. By the way. So let's imagine that. Let's imagine that you detected instantaneous center of rotation. Okay, let's assume that you detected instantaneous center of rotation of our body. For example, a pin. A pin is for sure instantaneous center of rotation, yes, of a body. Then you can replace this equation with such equation. Okay, I would like to underline one thing. You can replace it. Do not use these two equations together, yes? For example, look at the piazza, and there is, I think yesterday, there were like two posts saying that we come up with a set of equations, and all of a sudden we have 0 equals to 0. That's why, because they use these two equations simultaneously. Okay. Yeah. So what do we have in here? Instead of taking sum of moments about C, you can take sum of moments about instantaneous center of rotation, MA, yes? And then this will be equal to IA alpha body, where IA is moment of inertia about that instantaneous center of rotation. And you can find it using parallel axis theorem, or in some countries it is called also Steiner's theorem. For example, in Germany, yes, Anna, it is called Steiner's theorem, yes. I don't know, that's all. Any questions? Yeah. So just the thing you should keep in mind today is that sometimes when you see instantaneous center of rotation, you can forget about this equation, and you can use this equation. Yep. That's all. Can we do example number 1? Only 2 people are nodding, so we can do it. Okay. As usually, please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have a body of such odd shape. And what do we know about it? We know its mass and moment of inertia about C. We know where center of mass is located, which is great. We know geometry, yes, we know that this radius is R. And did they tell us that there is no slip? Yeah. Less impression minutes after release, the time in the following. Okay, let's assume that there is no sleep. Yeah, they told us that there is no sleep. Let's assume that. And we also know that our system starts from rest. Oh, what's going on today? Starts from rest. They ask us to find angular acceleration of the body in the position shown, plus minimum coefficient of friction to prevent sleep. Okay, let's do it. Since we are in kinetics of rigid bodies, we will just follow our recipe. Okay, we will start with FBD and KD. And today I want to use a trick. I'm just going to copy this drawing, paste it here, and paste it here. Check this out. I like 21st century, actually. It's saving time a lot. Okay, so I'm gonna go for easy forces, as usually. So I think that there is mg acting on our body. And I think that there will be normal force here, right? And what, friction? Friction acting this way. Okay, so I went for easy forces, and I think these are all the forces acting on our system, right? There are no other forces. Okay, so now KD. So in here we'll have MACX, MACY, and IC alpha. You know, guys, I changed my mind. I don't want to use alpha body. I'm just going to use alpha, since we have only one body, okay? So it will be just alpha. IC alpha. That's for clarity. Okay, we're done with FBD and KD. So now EOM, right? So EOM is following. Sum of forces in the x direction, sum of forces in the y direction, and sum of moments about point C. Yeah. Our knowledge about that instantaneous center of rotation we will use in the second example, okay? This one will be, in here we will continue what we learned the last time, okay? So what do we have in the x direction? Aha, minus TF. And this is equal to MACX. What do we have in the y direction? Aha, we have minus mg plus n. This is equal to ACY. Okay, guys, can you tell me anything about this ACX and ACY? Can we set up any of them to 0? Not really, yeah? Not really. Yeah, because AC is not located here. Sorry, the C is not located here, yeah? It is located here. These guys will not be 0. Yeah, ACX and ACY will not be 0. Great, okay. And how about sum of moments about C? Aha, we have two forces rotating about C. So we have N rotating in a positive way, so NR, and TF rotating in a negative way, TFR. And this is equal to IC alpha. Alrighty, we have 3 equations. Let's count our unknowns. This is unknown. This is, oh, sorry, this is not known. This is not known. N is not known. Oh no, it is also a 5th one here. So we have 3 equations and 5 unknowns. Not good. Okay, so what did we do last time to find more equations? We ran acceleration analysis, yes, on our body. So let's do it. Let's introduce more equations via running acceleration analysis. Okay. And we can run, and by the way, we don't know anything about any point, yes? So I propose running two acceleration analyses, okay? Let's do acceleration analysis between B and A. Maybe let me copy this drawing here. So this is A, B, and C. Yeah. So I propose running acceleration analysis between B and A, and then, I don't know, C and A. So what will we have in here? We will have AB is equal to AA plus alpha times RBA minus omega squared RBA. Okay, and I'm just going to copy this expression and paste it one line below, and I'm just going to change subscripts, okay? So this will be C, C, and C. And by the way, system starts from rest. Yep. So we can do exactly the same thing as we did last time. So this is 0 because system starts from rest. And this is also 0. Okay, so let's start with the first equation, this equation. What you guys can tell me about AB? So AB will have in general these components, ABX, ABY, and 0, but one of them will be 0. Do you want to tell me which one will be 0? Which one? Why? Yes, because trajectory of point B is this. This is trajectory of point B. Yep, so that means that this guy will be 0. Okay. Yeah, you didn't answer that because I asked that question to you like 7 times this semester. Yes, sorry for annoying you. I didn't want to annoy you. Sorry. Okay, and there is no sleep at point A. Yes. No sleep. So that means that only this component will be non-zero, right? Plus 0, 0 alpha times this vector, RBA. So I think it will be this vector. And that vector will be 0, R0. All right. So if you do this determinant, you will end up with minus alpha R 0, 0. And that means that our equation will look like that. Minus alpha R AY 0. Okay. And you can clearly see that from here, we have that ABX is equal to minus alpha R and AAY is equal to 0, which was expected because the system starts from rest. So there will be no centrifugal acceleration at point A. Okay, so we have our AB equal to minus alpha R 0, 0 and AA equal to 0 vector. Great. So now let's do our second acceleration analysis, unless there are questions. No questions. Okay, so now let's do this acceleration analysis. Oops. So in here we'll have ACX, ACY0 is equal to 0 vector plus 0, 0 alpha times this vector. Okay, let me scroll up the board and just show you this vector. RCA. I think that RCA will be here. This is RCA. And I hope that all of you see that this will be minus R, R0. Yeah, I believe so. Yeah, minus R, R0. Yeah. So let's plug this quantity in here, minus R, R0. And if you do this determinant, you will end up with minus R, minus alpha R, minus alpha R0. Great. So we found our two expressions, yes? ICX equals to minus alpha R, and ACY is equal to minus alpha R. So I hope that you remember that we left our system of equations with 3 equations and 5 unknowns. Now, triumphantly, we found 2 missing equations. So let me copy the system of equations we left earlier. This system of equations. Copy. And let me augment it by these 2 expressions. Okay, all of a sudden, we have 5 equations and 5 unknowns. Okay, I solved it yesterday. Yeah. And I'm just going, I bet that you know how to solve it, yes? Yeah, you solve it like 1700 times in your life, yes? So before I show you the solution to this set of equations, are there any questions to what happened? Yeah. I have one question. Am I talking too fast today? No, it's fine? Yeah. I have a strange feeling I'm talking too fast today. It's not, this is a strange feeling, yes? Yeah, everybody is with me, yes? On the same page, great. Okay, so this is the solution to this system of equations. So our alpha is 1/3 GR. Our TF is 1/3 mg. Our N will be 2/3 mg. And also our ACX and ACY will be minus 1/3 G and minus 1/3 G. Okay, so they actually ask us to find this only in part A, yeah? Let me scroll up the board. Yep, in part A, they ask us to find this. So we done with that. I mean, almost, yeah, because we need to express it as a vector. So our alpha vector wise will be 0, 0, 1/3 G over R. And this is positive value, so it will be counterclockwise. Yes, or so it will be which way? This way. Counterclockwise. Does it make sense if you look at the drawing, at the picture? Yes, it makes sense because mg will cause our system to rotate counterclockwise. Yeah, with this point as a support. Yeah, it makes sense. Okay, so before we do part B, any questions to what happened in part A? Okay, so now part B. Find mu(s) mean. Okay, so since we are in static friction range, we will use this expression: Tf lower equal mu(s)n. Yes, this is our inequality that rules this range. Yes. So my tactics yesterday was to take these findings and plug them in here. Okay, because we found Tf and n in part A. So let's just plug them in this expression from part B. So I would do, so that means that 1/3 mg is lower equal than mu(s), 2/3 mg. And many things cancels out, yes? I think that these 3 cancels out, mg cancels out, and we ended up with such expression: mu(s) larger equal 1/2. They asked us to find the minimal value of that mu(s), so it will be at the edge of that set, yes? So our mu(s) mean will be equal to 1/2. So this is answer to part B. Yeah. And for the 10th time today, are there any questions? Okay. So we killed example number 1. Yes? Okay, so what's the take-home message? Train that recipe. Yes? FBD, EOM, find additional equations, algebra. Yeah? However, I will ask you for maybe some extra homework problem. Yeah? Let's look at that problem. Can you detect instantaneous center of rotation on that picture? Question mark. This is a question, yes? Anybody want to collaborate today? You don't want to, yes? Yeah, go for it, yeah. Yeah. So if you would like to, at home, solve that problem once again, but instead of this expression, instead of this, find sum of moments about A. Okay? Sum of moments about A. Actually, we can do it here, yeah? So it will be only M, yeah, so A is here. So mg only rotates about A, yes? So in here we will have mgr, yes? This is moment about A, yes? And this will be equal to IA alpha. And I'm gonna mark A with red. It's not C anymore, it's A, yeah? So if you do that at home, and if you find this using Steiner's theorem or parallel axis theorem, you'll end up with exactly the same answer we found during our discussion. Okay, if you would like to, you can do that at home. If you would like to. Okay, was that clear? Yeah. So sometimes this is faster, you know, sometimes this is faster. Because you know why is it fast? It's faster because look, In here, we will find alpha immediately. You will know exactly what alpha is. It will be 1/3 GR, yeah? And in here, these are unknowns, you see? N and TF were unknown, yeah? So you have to exercise a little bit to find alpha. And if you go for this approach, you have alpha immediately. Yeah, you get rid of the unknown reaction forces from this equation. Yeah, just a digression. All right, example number 2 then. Let's do it, okay, but I will just erase this one, okay? Because you guys should remember that you should not use these two equations in one set of equations, okay? Example number 2. As usually, please read and understand the problem statement before we start our solution. Okay. Keep thinking, keep writing. I will keep talking, and then we'll have a poll, okay? Think about if you're gonna be for yes or for no. Okay, so what do we have in here? We have a bar, yes, of length L. Length L, mass M, and moment of inertia 112 ml squared. Our favorite moment of inertia, yes? We also are on Earth, so we have G. We know that the system starts from rest, which is great. And the question is, where to put that pin? Where to put that pin A? So that our beam has maximal angular acceleration. So in other words, how far pin A should be from the center of mass so that the angular acceleration is maximum. So maybe before we even start solving that problem, let's do that poll. How many of you think that pin A should be placed at one of the ends of the beam so that angular acceleration is maximum? Do you wanna vote, or you don't care? Like, do you want to? I mean, we can do it, yeah. I know. So okay, so in order to obtain maximum angular acceleration, we should put pin A at the end. Who thinks yes? Yeah. So wait a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 people. Okay. And now no. 1, 2, 3, 4, 5, 6, 7, 8. Okay. We have more than 18 people here. Who does not care about voting? I mean, me, for example. Yeah. Oh, no, everybody voted? Okay. Okay, so can one of you who said no, can you tell me why you voted no? Scott.
Yeah, well, I was thinking about a lecture yesterday with like the demonstration with the balls, and how if there's more mass towards like the other edges, they accelerated slower. So if the pin was in the middle, it'd be like the least amount of mass going out on the side. So I would think that would make it better.
Yeah, I didn't get everything. First of all, if pin is in the middle, that beam will not rotate at all. You mean if pin is here, you mean? Oh, no worries. But you voted correctly, yes? So, will, yes? Yeah.
I guess my thought was that if you have
Yeah. Well, we'll see. We'll see if this is true. Yeah. Okay. Anybody else has like good explanation why no is correct answer? So we will see after the solution. You will see why. Okay? Yeah. As you can see, democracy does not always work. Democracy actually works, in my opinion, only in one case. Food. If there is a restaurant and there is a huge line in front of that restaurant, that means that this is a good restaurant. Yes, that means that they serve good food, cheap, and big meals. Yeah, that's my opinion. Yeah, but this is dynamics. This is not Michael's thoughts. Yes, let's do dynamics. Okay, so we're gonna continue our recipe. Yes, FBD and KD. Unfortunately, that was recorded, so not good. They will shut up my channel. Okay, so I'm just gonna draw that beam twice, yes? I mean once, and I'm gonna copy it, of course, yeah. So this is our beam with center of mass. I think that center of mass can be a little bit towards the right, yeah, here. Yeah, that's better. Okay, so what do we have in here? We have mg acting this way, and we have reaction force, yes, at that pin. So we will have, I usually call reaction forces, I name reaction forces after the name of the point. So it will be AY and AX. But you can name them however you want, yeah. So AY and AX. And that's all, yeah? There are no other forces. Cool. Okay, and now in here we will have MCX, MCY, and IC alpha. Okay, we're done with FBD and KD. Now equation of motion. Sum of forces in the x direction, sum of forces in the y direction, and since we have a pin in here, and that pin is for sure instantaneous center of rotation, we will do sum of moments about our A for the first time this semester during our discussion. Okay, so in here we have AX is equal to MACX, and I forgot about A's in here, yeah? Now, how many forces act in the y direction? Aha, minus mg plus ay is equal to macy. And now there is only one force rotating about point A. And this is mg, right? And mg rotates in a negative fashion. So it will be minus mgh, and this is equal to IA alpha. Okay, and now let's use Steiner's theorem. So our IA will be equal to IC plus m distance squared, yes, so h squared. So that will be equal to 1/12 ml squared plus mh squared. Okay, so this is equal to m 1/12 L squared plus h squared. Okay, let's plug this value here. And I actually think that we need only third equation, yes? We can neglect first two equations, yes? I believe so, yeah? We will have minus mgh is equal to m 1/12 L squared plus h squared alpha. And m cancels out. Yeah, and we have expression for alpha. alpha is equal to minus GH L squared plus 12H squared times 12 in here. Okay, I don't like fractions. Okay, so this is our, so we expressed alpha as a function of that distance h. I hope I didn't make a mistake. No, it's fine. Okay, so we found alpha expressed as function of h. And I think that we should find the maximum value of alpha. Yes? Okay, so in your calculus class, how did you find the maximum value of alpha? Of function? Take a derivative, yeah. So we're gonna take derivative over h. So we're gonna have d alpha dh. So this will be, if I remember correctly, L squared plus 12h squared squared minus 12g L squared plus 12h squared minus 12gh times 24h. Yeah, I think this is correct. And we not only take derivative, we must equal it to 0. Yeah? So this is 0 when numerator is 0. Yes? And as you can see, our denominator cannot be 0. So it's great, because we cannot divide by 0. Okay, can I simplify that somehow? Let me see. Yeah, I think I can get rid of g. Yeah, so minus 12g L squared plus 12h squared plus 12g h squared times 24. So I think we can simplify it a little bit. Yeah, so I think that we can get rid of this 12. We can get rid of this g. And we'll end up with our equation looking like that. Minus L squared plus 12h squared equal to 0. Great. So that means that our h squared is equal to 112 L squared. Let's take let's take square root of both sides. So we will end up with h either equal to L divided by square root of 12, or h equal to minus L square root of 12. We got two answers. Yeah? Which is fine, because our system is symmetric. Yeah, the geometry is symmetric. So that means that maximum acceleration will be obtained if A is, for example, here, and also here. Yeah, it's symmetric. Yeah. So as you can see, guys, h is not equal to L half. Yeah, because if h is equal to L half, that means that it will be at the end. Yeah. So h is equal to L divided by square root of 12. Okay, let us find the maximum acceleration, and then we can think why it's not the end. Okay, it's not the location of pin is not at the end. Okay, so I have to take this expression, yeah, and I have to put it here, I think. I have to take that h, and I have to plug it here, right? So it will be L So alpha max will be this expression for h equal to L square root of 12. So this will be minus 12g L divided by square root of 12 L squared plus, oh cool, that will cancel out, L squared 12. Great. Oh, I didn't know that even. Bang bang. So in here we will have minus 6g L square root of 12. I believe so. So this will be equal to square root of 12 divided by 2 negative gl. Let me see if I got that yesterday. No. Oh no, I did, because this is square root of 12. Square root of 12 is 2 square root of 3. Yeah. So alpha max is equal to minus square root of 3 gl. So this is our alpha max. And also if we plug in, this expression for h equal to minus L square root of 12. So before we plug in positive value, now negative value, we will obtain alpha max plus square root of 3 gl. Okay, so just to finish that problem, let's do these two drawings. So this is our answer. So we will have our maximum acceleration obtained for this scenario and this scenario. So this distance will be exactly the same as this distance. And I forgot how much was the distance. L divided by 12 square root, okay. L divided by square root of 12, L divided by square root of 12. However, in here we obtained alpha max negative minus square root of 3 gl, and in here we obtained exactly the same value but positive. Alpha max is equal to square root of 3 gl. Yeah, but that was expected, yeah, because our system is symmetric. Okay, that's the end of the problem. Any questions? Yeah. So anybody wanna? So anybody had like a light bulb appearing above their head during this solution? Can you tell me why is it not at the end? So I know why you voted that it will be at the end, because you thought that the arm will increase. Yes, the farther from the center of mass we put the pin, the larger the arm of the moment will be. Yes, that's why you voted yes. That's correct. However, the farther we put the pin from the center, we also increase moment of inertia about the pin. So the larger the moment of inertia is, the smaller the alpha will be, yes? Yeah, because moment of inertia is like a resistance for motion, yes? So the larger the mass is, if I want to push something, the larger the mass is, the harder it is for me to push, yeah? The larger the moment of inertia is, the harder it is to accelerate that thing, yeah? So you see, so we have, so with increased arm, we indeed had increasing moment, but also with increasing arm, we have larger moment of inertia. So that's an optimization problem, yes? We must find the golden golden point, yes, which in this case was L divided by square root of 12. Was that explanation clear? I hope, yeah. Okay, and I have nothing else to say, so just enjoy your weekend. Yeah, thank you, bye. Yeah.